we have seen context-free grammars for representing context-free languages, and we defined a language as context-free when there exists a context-free grammar accepting it or generating it. And after context-free grammars, we have learned about push-down automata, and we saw that for many of the context-free languages that we saw, we have defined push-down automata. Now, an interesting question is, are push-down automata equivalent to context-free grammar? And the answer is yes. And today we are going to discuss a theorem which established that push-down automata and context-free grammars are equivalent in power for recognizing languages, and their equivalence is the topic for today. And we can start with the theorem which is proved by Chomsky, Ewey and Schurzenberger in 1962. And the theorem tells us the class of languages definable by context-free grammars and push-down automata coincide, which means for every context-free grammar there exists an equivalent push-down automaton, and for every push-down automaton there exists a context-free grammar. In this lecture, when I say push-down automata, I mean non-deterministic push-down automata. And this theorem can be proved using two claims. Claim 1. Given a context-free grammar G, we can obtain a push-down automaton AG such that the language of AG is same as the language of G. Yes, given a context-free grammar, we can obtain an equivalent push-down automaton. And claim 2 is the other direction. Given a push-down automaton, we can obtain an equivalent context-free grammar. And in this lecture, we are going to see the proof for claim 1. And the claim 2 will be proved in the next two lectures. So, claim 1 tells us that for every context-free grammar, there exists an equivalent push-down automaton. And as usual, we are going to understand the algorithm for constructing a push-down automaton from a context-free grammar. We are going to consider an illustrative example. Consider this context-free grammar for the language ANBN. And for the construction, I am assuming that the grammar is converted into Grayback normal form. So, here is an equivalent grammar in Grayback normal form. So, from now onwards, assume that this is what is given as grammar. Now, look at a string which is in the language represented by G prime. I should write it as L of G prime. So, A cube B cube is a string in the language of G prime. So, what would be the leftmost derivation, LMD leftmost derivation for A cube B cube? We know that the derivation must start with the start simple of the grammar, capital S. And if I apply production number 1, I will get ASB. Then because it is leftmost derivation, I am going to apply a production for capital S, again production number 1. So, this S will be replaced with ASB. Now, I am going to apply production number 2. 2 means this is the production. So this capital S is going to be replaced with AB. And now B is the leftmost simple. Only one production is this one, production number 3. When I apply it, capital B will be replaced with small b. Next, capital B, production number 3 will allow me to replace it with small b. And finally, again by applying production number 3, I can replace this capital B with small b. I am now deriving AQ, BQ. So this is the leftmost derivation and the only one in this example. Now the question is, can I simulate the leftmost derivation, that is this, with a push down automaton? The answer is yes, and that is why we are going to see, and later we will generalize it to generate a push down automaton from an arbitrary context free grammar in Grayback normal form. So we are going to see a single state push down automaton simulating the leftmost derivation. Here is the leftmost derivation. For this example, we are going to see how a single state push down automaton can generate this language or can simulate all possible derivations of this grammar. And that is true always. You can have a single state push down automaton. And recall, this is the grammar given, and we want to obtain a push down automaton. And the idea is to define a transition relation for the automaton from every production in the given grammar, and that is the objective. Later we can see how we can do it. So we need to see the derivation of this string AQ, BQ, and also we are going to see what will be the corresponding computation on the same input in the required automaton. We know that in the grammar the derivation should start with the start simple, and now I am going to apply production number 1. So before that, how will you represent this stage in the derivation? The stage is we just started. To start with, you have to start from the start simple of the grammar. Then what would be the corresponding configuration in the required automaton? Here is it. That means AQ, BQ is the input given, the only state, that is the start state also, read head to the first simple, and what is the top of stack simple? That is interesting. In the generated automaton, the bottom simple is going to be the start simple of the grammar. Remember, that is the case. The bottom simple of the required automaton is going to be the start simple of the grammar. Okay, so that is the initial configuration. And now I am going to apply production number 1. I will get ASB. And remember, now I want to generate AQ, BQ. The moment I applied this transition, I generated the first simple of the required string, and that is always the case in a Grayback normal form, because the first simple in the RHS must be a terminal simple. You can select a production whose RHS is matching with the first simple of the RHS. So I have generated this first simple, and that is why I have given red color to it. Now I applied production number 1, and I need to have a transition in the automaton. So we need to see how to define a transition from this production, and here is it. What is it? QAS, and that is exactly the configuration where you want to have a transition for QAS. And what is it? QSB. You know that there is only a single state, so the next state must be Q. And this is capital SB, and the question is, how are you getting this transition relation from the production? It's, you know that the only state is Q, so this is okay, this we know, the only state. And what is the input symbol? The input symbol is going to be the first symbol of the RHS of the production. Okay, small a, that is why small a here. And what is the top of stack symbol? Top of stack symbol is going to be the LHS of the production. Here the LHS is capital S. Always the LHS is going to be the top of stack symbol. And what is the RHS of the transition relation? It's a pair. We know that it is the next state which is always Q, so that is fixed. And a string which is going to replace the top of stack symbol. What is that string? The string is nothing but the string which follows the first symbol in the RHS. We know that it is in Greibach normal form. So, a terminal symbol followed by a string of non-terminals. So, whatever be that string, you take it as the second component of the transition relation. So, just do it mechanically and see what is happening. So, if you have this transition, if you apply it, what will happen? The state will not change because it is Q itself, and input read head will be positioned here and S will be replaced with capital SB. So, this is exactly what is going to happen. So, this input is read. So, this is the configuration. Now, I am going to apply production number 1 again for this capital S. So, this is what I get. And now, I already have a transition defined for the production number 1 which I applied. What is it? This is the transition. Apply it. What will happen? Read head will move to the right. This capital S is going to be replaced with capital SB. So, this is what is happening. And remember that at any point of time, and whatever is generated here as a terminal string is the past input for the automaton. That is always the case. And whatever be the string of non-terminals you have in the current sentential form is going to be the content of the stack, and that is always the case in the construction or in the simulation. And we can try to proceed. Now, I am going to apply production number 2. Production number 2 is this. So, what is it? Capital S is going to be replaced with small a capital B. That is what I did. S is replaced with small a b. Now, we need to have a transition for this. If you apply the same rule, what will be the transition? Q, the next symbol is A, the top of stack symbol is capital S. So, QAS. What is in the RHS? Q comma capital B. If you apply, if you remember that rule, that is it. The state you know, next symbol is this, top of stack symbol is this, that is capital S. And what is RHS? Q is fixed, and whatever be the string following the first symbol is this. That is it. So, if you apply this transition, you know that what will happen is this S will be replaced with capital B and this will move to the right. Okay. Now, I am going to apply production number 3 for capital B. This is production number 3. So, this B is replaced with small b. I need to have a production, I need to have a transition relation for this. What is it? Apply the rule. It is Q, next input symbol is B, and top of stack symbol is capital B. So, Q, B, B is what is in the LHS, and in the RHS it is Q followed by what? It is epsilon, because followed by B is nothing. So, it is epsilon. So, if you apply this transition, what will happen? You will move to the right, you will take out 1B. That is what is happening. And again I can apply production number 3, and I do have a rule for production number 3 or transition relation for production number 3. What I do? Move right and take out, because this is the transition that gets applied. And final stage in the derivation, I am applying again the same rule, deriving the required string, and here I have a transition relation for the rule. Just apply it and we are done. So, when you finish deriving a string, here you finish reading the input and finish the stack, and by empty stack you can accept, and that is it. And if you recollect what we did, this was what we did. So, at every stage if you look at, you can see that if you look at an arbitrary sentential form, A cube is what is derived, So, what will be in the current configuration, the remaining input will be, after removing AQ from the input, whatever is the string. So, it was actually AQ BQ, AQ is read, and so the remaining string is BQ, and whatever be following AQ which is derived is going to be the stack content, and that is it. Hope you remember it, otherwise watch it again and see. And this is what we just discussed. If this is the sentential form, what will be the corresponding configuration? That means the input processed so far is AA, and the remaining input will be there, that is 1A followed by 3 B's, and SBB will be on the stack. So, this is the configuration. From AQ BQ, AA is processed and SBB will be on the stack, Q is the early state, and the read head pointing to the next symbol in the input, and that is it. And you recall how we defined a transition rule from a production, and suppose this is the production. In the LHS capital X, in the RHS small a followed by a string of non-terminals. If you recall, what was the transition required? From Q, if A is the next input symbol and X is top of stack, what do? You remain in Q and replace the top of stack symbol X with this string, and that is what we did. And now this is enough for us to formally write the algorithm. We can try to do that. Given a context free grammar VTSP, V is the set of non-terminals, set of terminals, the start symbol, and set of productions. We can define the push down automaton AG such that their languages are same. And how will you define the automaton is the question. Now, without loss of generality, assume that each production is in Grayback normal form, that is LHS is a non-terminal or a variable, RHS is a terminal symbol followed by a string of variables. Why without loss of generality? Because we know that every context free grammar can be automatically converted into Grayback normal form, and that is why I write it as without loss of generality, I can assume. Now, here is how you can define the automaton AG, that is a tuple. Do not worry, I will explain. What is this? The only state in the automaton, it is a single state automaton. And what is T? T is the set of terminal symbols of the grammar, which is the going to be the input alphabet for the automaton. And what is the next component is the set of variables or non-terminals in the grammar is going to be the stack alphabet. And next is the start state, the only state is going to be the start state also. Later we will define the transition function, and the last component is the bottom of stack symbol, which is nothing but the start symbol of the given grammar. And now it reminds us to see what is the transition relation. The transition relation is defined as, it should be relation is defined as this. If you have a production X going to small a followed by this string of non-terminals in P, then what do you want to have here? From Q only state, next symbol is small a, top of stack symbol is capital X. In the RHS, the only state followed by this string. That is exactly what we saw. And this is the construction, which is simple, and you can have a claim for the correctness of it. You can prove it, the soundness and completeness, by the principle of mathematical induction. And with this, we are moving on to the last slide in this lecture, where I am giving you a practice question for you to test the algorithm. So, you apply the algorithm that we learned to obtain a push down automaton from the context free grammar which is given to you, not that this is already in Grayback normal form. And after finding the automaton, you also simulate the obtained automaton on this input. So, today we have seen the Chomsky-Schutzenberger theorem. Chomsky, Ivy and Schutzenberger proved in 1962 that context-free grammars and push-down automata are equivalent in power for recognizing languages. So, today we have seen the proof that for every context-free grammar there exists an equivalent push-down automaton. Please try to solve the practice question and understand how the algorithm works. Thank you.